Moving right along, we'll just touch on this energy transport idea, which we have already discussed. We talked about excess energy in the low latitudes and deficit energy in the high latitudes. So when we look at zonal mean meridional transports, we can obviously derive how much energy needs to be moved to balance the energy deficit from the energy surplus, which turns out to be about 6 petawatts away from the tropics into higher latitudes. How does it actually occur in the ocean and the atmosphere? There are details, but it turns out that Hadley cell doesn't do that much of an energy transport, especially because you can see that air is rising in the warm region and moving energy here, but actually energy is converging back from the colder latitudes into warmer latitudes here. So the net energy, when you include humidity, does occur northward, but most of the work in the low latitudes is done by the ocean, it turns out. So you can see this area under this part here is much larger for the ocean in low latitudes compared to the atmosphere, but the ocean transport goes to zero at some latitude here in the mid latitudes, and the atmosphere has a huge area under it. So most of the energy from mid latitudes beyond the Hadley cell towards the poles is done by the atmosphere. So even though atmosphere has very low density, very low heat capacity, it moves fast and it moves a lot, so it does do transport. And it turns out, dynamically speaking, most of the flow is very strongly zonal because the Coriolis is strong in the mid latitudes. Remember, it increases from the equator towards higher latitudes, so it forces the flow to be very zonal. So westerly winds, as we will see, are very strong, and yet there will be eddies. There are eddies which do northward transport because these zonal jets are basically unstable, and there is a lot of eddies which can move heat into the polar regions and do the work that needs to be done. But nonetheless, looking at the mean, this is what we get. So estimated total poleward heat transport in petawatts, so that's 10 to the 15 as a function of latitude by the atmosphere in the dark gray line and ocean in the black line, and the total required poleward heat transport based on top of the atmosphere energy balance that we had looked at before, and here it is again in the gray shaded area. Poleward heat transport is defined as positive northward, so negative heat transport indicates southward transport. Basically, that means heat is energy is diverging out of the low latitudes towards both the poles, as you can expect. If you open up the zonally averaged flow, you get the zonally asymmetric or non-axisymmetric flow, or the response of the atmosphere, which can be seen as the vertical motion in the pressure coordinate, which is a good indicator of the convection, for example, and the vertical meridional velocity. Let me make sure again. At 10 meter meridional wind and sea level pressure here, and surface temperature. Okay, so you can see the zonal asymmetries, which basically means if dx of anything is not zero, we call it zonally asymmetric flow. Axisymmetric means when we zonally average things, we assume that zonal asymmetries are not so important or averaged out, but obviously when we open it like an accordion, there are a lot of zonal asymmetries, of course. Okay, so boreal summer climatology over 1981 to 2010 of pressure vertical velocity at 500 millibar, which is kind of the middle of the troposphere for a convective region and is a good indicator of large-scale atmospheric flow. Just take it from me. And here, because it's in pressure coordinate, omega is typically written in pressure per second, so pascals per second. 10 meter meridional winds in meter per second, and surface temperatures TS equivalent to SST here, and did I jump? Yeah. So this is the sea level pressure in hectopascals. Red indicates descending motion here. So where we had high OLR, cold temperatures typically have subsidence, and of course in the Hadley cell and the subtropical gyre as well. And the deserts are formed because of subsidence and negative omega that brings clear skies, no rain, no clouds, and actually nice weather if you like that kind of sunny weather. And that's the Mediterranean weather over there. That's the monsoon climate over there, the ITCZs with strong W's. Why is W negative in the upward direction? Because pressure decreases in the vertical, so P dt is negative as you go up. So wherever there are strong convections like the Western Pacific, you expect strong negative omegas, as you can see here. So again, subtropical gyres and deserts and Mediterranean climate, and cold temperatures here because of the Somali upwelling on the annual mean. Okay, so meridional velocities, strong trade winds, south easterlies become northerly meridional winds, southerly meridional winds. Here the along the western boundaries of the ocean you have strong southward, and obviously they become westerly here in the zonal direction. So you can see okay, so make sure we have the directions right. Okay, so sea level pressure, obviously you have seasonal changes happening, but you can see the lows and highs related to the subtropical gyres, and the southern ocean band is slightly different than the northern band, and the monsoon region is different here because this is boreal summer climatology. So the monsoon rainfall has the monsoon trough and the low pressure and the Tibetan high here, and surface temperatures, you get on land the cooling, cold temperatures and high pressure should correspond. Low pressures and warm temperatures should correspond, cold temperatures and high pressure should correspond, and so on and so forth. So all the consistent features happen. So these are kind of these show the relation between the ocean and the atmospheric response to the ocean forcing. And of course it's a coupled system because the atmosphere is forcing the ocean. For example, strong winds are creating upwelling here, converging winds are creating low wind speeds, low latent heat loss, warm sea surface temperatures here, and rainfall and freshwater flux obviously makes the mixed layer shallower and warms it further by trapping the energy, and so on and so forth. So the ocean atmosphere interactions can be easily seen in these kinds of plots that are very instructive if you remember how to interpret the ocean and the atmosphere together. Maybe I'll stop this here. It's maybe a little bit short, 8 minutes, but that's okay. We will come back and look at the zonal circulation, which is also part of the zonally asymmetric response, but puts this vertical velocity and pressure distribution in a better context. And then we will look at the winds, which will prepare us to again revisit El Nino and some of the feedbacks that happen between the ocean and the atmosphere, so that we can move to coupled climate in the next chapter, after looking at ocean's response to wind forcing. Okay, this is very critical as well to understand the distributions of sea surface temperatures. We have done heat budgets, salt budgets, momentum budget, and so on, but we haven't actually looked at the comprehensive response of the ocean to wind forcing, which we will do first before we look at the coupled climate, and then come back and look at buoyancy forcing before we look at ocean's role in climate change. Okay.